So we're doing some stuff on AC power analysis today, and let's see, I downloaded this thing. There it is. And I have an animation that wants to run in Firefox. I'm not sure I have Firefox. Because Chrome security prevents apps from running anymore, which is really annoying. Maybe the Firefox now does too. There's been some updates. I thought I copied that. So right click, copy link address. Here, and I go to there, and there it is. And these are nice, really simple simulations. What I should do is I should make a video of these things because they're not going to be available forever. In fact, it looks like it's not available right now. So yeah, stupid security rules, stupid people making viruses. I don't know if I can find that, so I won't. You know, I wonder, I bet someone has a YouTube video, AC power. Well, I don't really want a whole course. I just want a really quick demo, but we'll just work it out. You'll just get an idea of it through the lecture. So, and maybe tomorrow I'll have something in the lab. We're doing a lab tomorrow on measuring impedance, which I understand you did already in physics, but I think everybody. We're going to do it. So we're looking at power. This is actually one of those things that, you know, this course serves many needs. If you're taking a course in electrical engineering, you might not get this so much. I didn't really get too much of this when I was in school because I was a double E major. But this is sort of the one thing that all branches of engineering should kind of be aware of, how power works in AC circuits. Kind of because if you're going to be a mechanical engineer, you're going to be working with machines that are taking power. If you're going to be a civil engineer, you're going to be working with machines that take power. You're going to be putting in power in buildings. If you're an electrical engineer, you're probably going to be doing something with power, but maybe not. If you're working with little microelectronics and stuff or digital, you might not be using this stuff. But in general, this is the kind of thing that that everybody sort of needs to cover. So that's why we're covering it in this class. We're going to learn how power works in AC circuits. And we'll be using complex numbers again to make a sense of, it turns out that power is actually described really well using complex numbers, just like phasors are, because of the way they actually work really well with AC circuits. So we start with the basic definition of power. If the voltage across a resistor is a sine wave, so right here's a resistor, and here is your VR of t, right? Well, there's going to be an IR of t, right? That equals VR over R, and the power is going to equal IR times VR, right? Or you can also think of it as just VR squared over R, because IR equals VR over R, right? So that's going to be your power. Now the trig gets really kind of convoluted here. We're going to do some of it. I'm going to want to make sure I don't run over anything later. And we can think of power as instantaneous power. Actually, I think it's a lowercase p when we do this. I made an uppercase p there. So turn your uppercase p into a lowercase p. Because capital P means something else. we're going to have a lot of new symbols, a lot of new concepts and stuff in terms of power. But what it comes down to is, Vm is the magnitude of the sine wave, right? And it's happening. It's oscillating at a frequency omega. So you would take Vm and square it, and then you also have to square the cosine, right? Cosine squared of omega. And then all that's going to be divided by r. And the trig formula, these trig formulas, right? The cosine squared omega t equals 1 plus cosine of 2 omega t all over 2. And basically what that is a raised cosine, right? So that equals, so if we take that and we use that trig identity, we can say, well, that's just Vm squared over r times 1 plus cosine of 2 omega t. All over 2. And what that actually looks like. So if you think about it, here is I'm going to do this. So I'm going to draw this as a so we're going to draw 2 curves here. The first one is going to be the cosine curve, which looks like this. Kind of hard to draw these things. And this is p r of t. No, sorry, that's not. That's v of. That's sorry. It's v of t. That's vr of t. The voltage can go negative, right? It's a sinusoid, and sometimes it's positive, sometimes it's negative. It's a cosine wave, right? Cosine starts off at 1, goes to -1, right? But the power, though, is the square of that divided by r. And for the power, I'm going to use another color here, which is going to be blue. And what that does is it makes something that's going at twice the frequency, but it's also raised up by a half. So essentially, if r is 1, then this would sort of look like this. So what would happen is it starts off at 1 here, and it goes to let's see, when it's 0 here. Wait, when that's 0, you're going to be 0. Well, actually, when it's here, this is better. When it's negative here, it's going to be back to being positive again here. So yeah, it's going to go like this. It's going to go. It's a little hard to draw these, right? But you do a dot, then you're going to have a dot right here, and then another dot is going to be here, and then you're going to be back up here, and then you're going to be back up there, and then you're going to be back up there. So it's going to look something like this. It's going to look. You've got a cosine that's going at twice the frequency. Because the power is the squaring of the voltage, right? So the power is sort of, and this is actually what's happening right now with these lights. These lights are actually flickering in the room, and they're giving us power, but it'll give power whether the polarity of the voltage is going positive or negative, right? It's going to emit power, but it's emitting power. If the voltage is oscillating at 60 hertz, what's the frequency of the light flickering going on? Yeah, it's 120 hertz. It's going to be oscillating at twice that frequency because the power, the light can transmit whether the voltage is positive or negative. It's going to just be blasting out light. But then when the voltage crosses 0, the power drops to 0, right? So it's flipping at twice that rate. So this is our little PR of t. Of course, assuming r is 1 and all that stuff, so the magnitudes don't get all distorted. It has twice that frequency, and it's offset by 1/2. That's this 1 plus cosine. It's a raised cosine. And it never goes negative, right? The power is always positive or 0 for a resistor. Okay. Now, what's interesting to engineers is what's the average power, right? If you're going to do all that thing, what's the point of this 120 hertz thing? We really want to know on average how much power are we getting, because sometimes it's high, sometimes it's 0. So for most purposes, what we're interested in is P average. And average power is that's a capital P. It's defined as 1 over T times the integral from 0 to T of our lowercase p of T dt. You want the average power? You take and integrate it over one period of that sinusoid, and you divide it by the length of that period. And what you end up getting is, well, we're going to have to do this. We're going to do 1 over T times the integral from 0 to T of Vm squared over R, and then times 1 plus cosine of 2 omega T over 2 dt. And well, it turns out that the cosine has an average of 0, right? If you integrate a cosine over a whole cycle, half the time it's above 0, half the time it's below 0, and those things add up to 0. It cancels out, right? The average of a cosine is 0 over one period. Cool with that? Yeah, but you still have this raised part here. So that raised part gives you an average, right? And that actually works out to just be Vm squared over 2R. Basically, it's the integral of 1/2 for t seconds divided by t, right? Well, the integral of 1/2 for t seconds, the area that's going to be t times 1/2 divided by t is just going to give you 1/2, right? So it's 1/2 of Vm squared over R, which we're multiplying it by. Did I go too fast? Does that make sense? Can you, sorry? The 1 over t is outside the integral, yeah. But the integral of this thing is going to give you basically 1/2 t. And then you divide it by t, so you end up just getting, well, it's going to be Vm squared R, sorry. Vm squared over R times 1/2 t. You pull the Vm squared over R out of the integral as well. But the integral of this thing, because this basically has an integral of 0, and this has an integral of 1/2 t. Yeah, the 1/2 remains. And basically what it's saying is, you want the area of under this blue curve, right? The area under this blue curve, when you go a full cycle, you could kind of convince yourself, I'll shade that in, the area under that blue curve for a full cycle, that would mean like going from here to here, right? It would be this area. Oops. It would be, yeah, it's the area of this part here, right? And some of the time it's below 1/2, and some of the time it's above 1/2. But on average, it's at 1/2. You can even see, you could take this chunk here and rotate it and flip it, and it would fill this gap right here, and take this chunk and rotate it and fill this gap. And you basically have a steady line there at 1/2. Probably confusing the hell out of everybody. I've just proved graphically that that's the average. Average power is that 1/2 line because it's stationary. That's where it's sort of oscillating about. And so we have this notion then that the average power is Vm squared over 2R. And there's this other thing that we define here, which is we define an RMS power. Now, if you if you define VRMS, so So RMS is this thing. These things are kind of jumbled together here, but basically, you can think of it another different way. Is P average? It would be nice if we could talk about P average, because you got this VM squared over 2R, and if we can get rid of that 2, if we can make this new term, and we just talked about this sort of what's the effective voltage squared over R, it would look kind of like DC power. So right, AC power is if you've got an AC sine wave with a magnitude of VM, then you divide it by 2R, you square it divided by 2R, that's the average power. But DC power would just be VR squared over R. So if you think about average power in terms of, well, what's that? So you've got a sinusoid of magnitude VM, and the power is VM squared over 2R. Well, what would be the effective power if you thought of that as like a DC voltage? And you could think of that as, instead of V effective, there is a term that does that V effective for us. It's called VRMS. And the RMS power is sort of has an averaging effect sort of built into it. VRMS squared over R is the same thing as VM squared over 2R. And that's only true if VM is, or VRMS is VM over root 2. And what is this RMS thing? Let's talk about that. So RMS stands for, if you're ever going into a lab or whatever, and if you're doing measurements of science, you might run into this. Sometimes you want to know what's the root mean square of the wave. And the root mean square for a V of t, where suppose V of t equals some VM cosine of omega t plus theta. Again, it could be at any angle, any phase angle that you want. And well, first of all, you square it, and that gives you V squared. Then you take the average, okay, and that gives you 1 over t times the integral from 0 to t of V squared of t dt. And then you take the root of it. So you take the root of it, and you get basically the definition of RMS, which is 1 over t, the square root of 1 over t times the integral from 0 to t of some V squared of t dt. Okay, so we call that root mean square. And what's interesting about root mean square is if you take the root mean square of the AC voltage waveform, then you can find power by just taking V RMS squared over R in a similar way that you would for a DC voltage. And so what we talk about when we talk about VRMS, that's sort of like the effective power, that's the effective voltage that gives you essentially what the same power that you're getting from the AC signal as it was. So like if you had, so basically, the way I like to think of it is, as an example, okay, suppose let's put an example here. Suppose you have a sinusoid of, well, suppose you look into your, what's the voltage coming out of the wall? Suppose like the voltage coming from the wall is what? That's a function of time. It's going to be what? What's the magnitude of that voltage? Anybody know? Yeah. 110 volts, 120 volts, yeah. 110, 120, something like that, right? Let's just say it's 110 volts. And omega is 2 pi times 60 hertz, which is 377. And maybe it's got some phase in it, right? Well, what this is saying is that's the wall voltage as a sine wave, right? And the power, if you run this across a, let's just say R is 1 ohm, right? Let's just keep it kind of simple. R equals 1 ohm, and you're running that 110 volt source across a sine wave across a 1 ohm resistor. Okay, how much power are you going to get out of that resistor? So PR, and we'll talk about the average power, P average for the resistor is going to equal the magnitude squared over 2R. It's going to equal 110 squared over 2 times 1. Right, so what's 110 squared? Well, 100 squared is going to be, well, 11 times 121, right? 11 times squared is 121, so is that going to be 12,100? See, you're an engineer, you can do all these calculations in your head. I was just actually I just had lunch with a friend of mine who's an engineer. He's an electrical engineer. He's the same age as me. He had a brain aneurysm like about 13 years ago. He had a stroke. Brain aneurysm is like, yeah, your brain starts, I think, pops a blood vessel and you get bleeding in your brain. And he almost became a vegetable. He lost a lot of cognitive ability. Well, they were giving him all this tests of like, they would give him these tests of like, Joe Smith kind of came in and did this, and then they would actually distract him with more information. Then they go back and like, what was the name of that person who came in and did this, in part of this dialogue? He couldn't remember any of that stuff. But then they would give him like lists of numbers, and they would give him lists of like 14 or 15. He could remember like 14-digit numbers. He couldn't remember like the names of people that they were describing, in this test. But part of the test was numeric, and they were blown away by this. They're like, how could you remember all these numbers when you can't remember all these names? And this one doctor actually accused him of cheating on this cognitive test. He's like, Tom, I'm like in a wheelchair. I'm slumped over. I can hardly move. And he's accusing me of cheating on this cognitive test. Like, how would I even do that? And I'm like, I'm an engineer. He's like, I'm an engineer. I used to be a parts manager for Ford. I knew all these, I had this elaborate numbering system. I knew all these things about numbers. Yeah, it was really funny. But you get so used to working with numbers as an engineer that all these things, they just never go. Even when everything else goes, you'll still be able to calculate stuff. So 110 squared is 121, is 12,100 over 2. So that's going to be like what, 6050 watts, something like that. It's going to equal 6050 watts. Does that sound right? Let's just assume it's right. 6050 watts. Okay. Now, if you might be wondering, okay, so that's if I plug in the sinusoidal signal there, right? It's 6050 watts. Well, what's VRMS? What is the RMS voltage of a sine wave? So let's just go over here. A sine wave of this voltage means that VRMS is going to be 110 over square root of 2 of that. So this one, I don't think I can do this one in my head. So it's going to equal V. It's going to be equal to 110 over square root of 2. That's the definition of RMS. 110 over the square root of 2. Actually, I want to put a VRMS. Well, let's just put this equals VRMS. I'm kind of winging it here. So 110 over root 2 is VRMS. So somebody figure out what that is. 110 over square root of 2. What is that? What'd you get? 77.78. Okay. Now, if you take 77.78 and square it and divide by 1 ohm, you should get 6050. Is that right? You want to try that? 77.78 squared. No, just divided by 1. That's the beauty of RMS. So the RMS sort of takes in the fact that what it's sort of saying, and this is what I like about RMS. It's sort of like saying, all right, so you've got a voltage here that's, oh, you look pretty proud of yourself. You got a voltage that can go up to 110 volts, peak to peak, right? It goes from 110 to minus 110. But a lot of times that voltage is actually going through 0, right? It's a lot smaller than 100 volts. But if you're thinking about it from a power perspective, because you're going to square that thing and then divide it by 2R to get the power, you know, the magnitude squared divided by 2R. Well, if you think about it as what really, if you had to come up with an equivalent DC voltage that would give you the same power, you would set it to this 77 volts here, the VRMS value. And if you plugged in a DC voltage at that RMS value across that resistor, you'd get the same power out of that resistor, right? Because the DC power is just V squared over R. AC power is V squared over 2R. You want to know what's the equivalent voltage if you had a DC voltage to get the same power? It would be 77 volts for a 110 volt AC signal. Because most of the time you're going through 0, so you're not getting a whole lot of power when that's happening. That makes sense? So that's what I'm actually saying for VR. What VRMS sort of gives you is the effective voltage. It's like the effective DC voltage to get the same power as an AC signal at a certain magnitude. And this VRMS is 1 over root 2 for a sine wave. I didn't prove that to you, but you can probably prove. I think there's a homework question about that. And it only works for sine waves. If you got triangle waves or square waves, RMS is going to be different. But when you have a sine wave, it's going to be square root of 1 over t times that voltage square root of t. Well, we just kind of showed you that that's this thing here. So basically, what we did when we computed the average power here, we had Vm squared over 2R. Well, that's that Vm squared over 2 is essentially the average of this sine wave, and the R is just there because we're trying to calculate power, right? Well, the average of this sine wave, Vm squared over 2, if you take the square root of that, that's RMS, and that's basically Vm over root 2. That's the definition of RMS for a sine wave. Okay. Hopefully that doesn't blow you away. We're going to play around with that in the lab tomorrow. We're going to be measuring these things, measuring RMS voltage and stuff like that. But those are, so this is, oops, this is, you could write, continue. This is sort of the V effective squared over R. So in other words, you want to know what the average power is for an AC signal. You know the magnitude, it's going to be Vm squared over 2R. If you know the RMS voltage, it's just going to be the RMS squared. And yeah, so I had a nice. This is what I was scanning my my stuff from last year. This actually. Do you have an extra sheet on your? Do you have a blank page now on your notes or no? Did I not give you? Did you not get the notes? I was real scared because I was like, at the last second before lecture, I'm scrambling because I like, oh, there's this big hole in my lecture notes. And I had to grab screen captures from my lecture last year from the video, which is pretty funny. And anyway, you're not going to have time to write all that stuff that we wrote on the first slide. That was a lot of stuff to write. But what I did was I actually expanded that. And this is actually probably more important on the next page, or maybe if you can find some room there. I don't know if your slides have that extra page or not. I think I just added that later. What you can do is, I think I have to do some surgery on this lecture. Here's our V of t, and because you probably don't have enough room here, our V of t is a sine wave. Sine wave that kind of goes off the rails there. Okay, that's more or less of a sine wave, right? And Again, in this case, suppose Vm here, which is the magnitude of that sine wave, is 10. For example here, a little bit easier to think about 10. The V RMS is going to be Vm over 2. It's going to be 0.707. And so PR, and I suppose it was going into a 50 ohm resistor. The P resistor is going to be V M squared over 2R. In this case, it's 10 now, yeah. It's going to be 100 divided, well, Vm squared over 2R is going to be 100 over 100. Wait, what? Yeah, it's going to be 100 over 2 times 50, so it's going to equal 1 watt. But it should also equal VRMS squared over R. And VRMS squared is going to be, well, what's 0.707 squared? That's, sorry, it's 7.07. 7.07. 7.07 squared is 50, right? So that's going to be 50 over 50 again. So again, that's going to equal 1. So again, the V effective, which is this VRMS, is going to be at 7.07 or so, right here. This tick mark is 7.07. And so basically, this is what I like to say, the power delivered by a 10-volt sine wave is equivalent to the power delivered to the same load by a 10 over root 2 volts DC voltage. The same R. That's why we like the RMS value. It's a nice, convenient way because it kind of gives you the equivalent DC voltage that you would need to get the same power from a sine wave. Okay. Now, oh, that was blank because I'm going to have to delete that, because that was a slide that I have to write on. So I hope you all got that down. Maybe I can put this somewhere else. I'll stick it over here. Maybe I can use it there. Now, what about inductors and capacitors? Okay, this is where it gets a little bit interesting, because with a inductor, and you have an IL going into an inductor, it's going to have a VL that induced across it, and we know that VL is going to be L di dt, which is going to be minus L times the magnitude of the voltage times omega sine omega t. Okay, that's if IL equals, right here, this thing here, Im cosine omega t. Then the derivative of that's going to be Im times omega times the sine, with a minus sign in front of it, right? That's going to be Im omega sine omega t, right? And so that's going to equal minus omega L Im sine omega t. So the power for the inductor, and again, this is the instantaneous power, is going to equal IL of t times VL of t. And that's going to equal minus omega Li m squared sine omega t cosine omega t. The product of those two voltages and currents. And that is going to equal minus omega L Im squared times 1/2 sine of 2 omega t. That's that double angle formula thing. I don't know. Unlike the trig identity, right, to go from one of those to the other. The product of two cosine alpha sine alpha is like 1/2 sine of double the angle. And what's the average power of that? What's the average of that? It's just a sine wave. It's not raised anymore. What's the average value of a sine wave? The average value is 0. Yeah, that's what the average power is going to be. It's going to be 0. And you can again draw a picture of this, and it shows you the in this case again the current now is a sine wave of magnitude Im, and I'm going to just sort of sketch out this thing here. It's going to go through 0. It's going to go negative. It's going to go something like that. Go up to there. So I'm going to go like that. It's helpful to learn how to draw a reasonably good sine wave. It just comes in handy so many times. So that's going to be our I, or our IL. Now the power is going to be going at double the frequency, but it's still going to be averaging 0. So it's going to be climbing up to some point and then back down to 0, and then back to 0 here, and then back to 0 here, and back to 0 here. So it's going to be looking like this. Twice the frequency, but still an average of 0. And similarly, for a capacitor, IC equals C dV dt, and that's going to equal minus C times Vm omega sine omega t, and it's going to equal minus C Vm sine omega t. And PC of t, lowercase, is going to equal IL of t, IC of t, VC of t, and that's going to equal minus omega C Vm squared.
What's that second line you wrote?
Times. Pardon me?
What's that second line you wrote?
Minus C Vm sine of, oops, did I lose an omega there? I think I lost an omega. Minus C. It's minus, right, IC minus omega C Vm sine omega t. Yeah, just move the terms around a little bit. And so we multiply that into sine of the cosine, and we end up getting, oops, it looks like I actually sampled my screen a little bit too soon, so I don't have the rest of that equation. But it's about the same thing. The power is going to be, although I think it's actually positive, so there's a sign flip, and I'm going to just guess this. It's going to be something like, I'll fix this tomorrow or later. It's going to be something like, maybe we'll just go on. It's going to be something like, I think it's going to be like omega C Vm squared times 1/2 sine of 2 omega t. Something like that. That's my question mark. So I'll come back to that. It's very similar, but because the you know, because of the relationship, because I equals C dV dt for LD I dt, yeah, maybe it comes out to be the same, but I think there's a sign flip that because the power for an inductor, oh, I think it kind of goes, it trends the opposite way. So there's like a 180-degree sign flip. So for a capacitor, I think it would be something, but I'll come back to that. It's a little tricky. I don't want to give you a wrong equation, so I will come back to that. So fix this. I think we can go out anyway. There's a lot of this hairy kind of stuff here. And in general, if we can actually crank this thing out, let's see. Yeah, this slide is so busy. Well, this actually might work okay. I have more junk on here than I need to. That if we talk about, in general, some passive linear network which has some, you know, L's, R's, and C's in it, which is going to have an equivalent impedance of, you know, some R plus JX, which is going to be, you can think of that as some magnitude with an angle of theta, and you can think about that as a triangle, which is going to have the magnitude Z on the hypotenuse, R on the real axis, and X on the imaginary axis. That that P of T, so if you've got a voltage I of T, or current I of T, which is Im cosine omega T, oh, there's a bit of a screwy thing on here too. Let's see here. Cosine of, one of these flip. P of T is, see, does it matter? Kind of doesn't really matter, does it? But it should. Oh, that was a T plus theta. Oh, I see. Yeah, I think I scratched it out of mine. So yeah. So you're going to scratch this out so it looks like the slides I have. It's going to be, make this say I am cosine of omega t minus theta, and make this say Vm cosine of omega t. We're just shifting everything up by shifting everything back by theta.
It's actually, it already is that on ours.
Oh, okay, it's just mine that's messed up. Okay, that's another slide I got to fix. That's for me. So the instantaneous power is P of T equals V times I, which is going to equal the product of those two, Im Vm cosine of omega t times cosine of omega t minus theta. And there is another trig identity which tells you, I'm not going to develop all these things, I hope you don't mind, that this cosine omega t minus theta, this thing here, can be written as cosine omega t cosine theta plus sine omega t sine theta. That's a trig identity, which I'm not going to derive for you, but hopefully you can trust me on that. But that allows us to expand this as Vm Im cosine of theta. So the cosine theta comes out, which is kind of, oh no, sorry. The Vm Im square bracket, cosine of theta, cosine squared omega t plus sine theta, sine omega t, cosine omega t. So it's turning into a really hairy kind of formula, but And again, we can use another trig identity that says, yeah, there's another trig identity. We're gonna, I'll plug that in a moment. But this can be reduced with a couple other, with another trig identity, or to a VMIM times the cosine of theta times 1 plus the cosine, you follow me? Okay, 2 omega t, again, that double angle thing, over 2, plus VMIM sine of theta times sine of 2 omega t over 2. Ollie, you're on the roll there, good. And this is actually a good thing to study because it's a mess, but we can pick out some interesting terms from there. And since we're kind of running short on time, what we talk about, I'm just going to kind of write this down really fast and we'll kind of pick it up next time. The average power. So this is on any general AC circuit. You can see there's going to be an average power component there. The average power component, we'll see the average power of this right term is just sine of 2t. That's going to be average of 0. But you're going to have an average component on the left term because you got that 1/2 in there. So the average power is going to be capital P is going to be VMIM over 2 cosine of theta, and in watts. And that is also going to be the same as these effective RMS values, V effective, I effective cosine of theta, which is kind of cool. And then we're also going to have this, this term Q. You know the term mind your P's and Q's? This is kind of what it's all about. Q, which is VMIM, I'm just kidding, VMIM sine of theta over 2. That's this term here. Let's see, that's this thing right here. That's Q. And that is going to equal V effective, I effective times the sine of theta. And this new term Q is the reactive power. It's not like activation energy, it's just reactive power. And the units are in vars. VARS, which stands for volt amp reactive. I love that with a flourish, the screen just disappeared. Volt amp reactive. So we'll explain what that is later. But what the Q is sort of like the power that's sort of it's being stored temporarily and then dumped back into the system. Because the L's and the C's, they don't actually absorb energy, they just store it and then they throw it back in the system. And you can kind of see that back on this chart here for the inductor, that green sine wave. When the green sine wave is positive, it's absorbing power, and when it's negative, it's pushing it back into the circuit. But that reactive power, we sort of need to account for that because it does require current and stuff to kind of flow into it and out of it. So we have to kind of keep track of that thing. We can't ignore it completely, but we're not actually getting anything useful in terms of work from the reactive power. The only thing that we can actually use, the power that we actually use for whatever we want to do, is the average power. That wasn't as bad as it could have been, I promise. So we'll talk some more about this, and I'll fix those mistakes I had earlier. Sorry about not giving you the handouts. Just kind of blinked on that. Perfect. Okay. Did you get any? If you came in late, you might have some homework there. Oh, and I have guys. Volleyball. And volleyball, yeah. Doesn't this make you want to play volleyball? All this stuff. You guys have my email, right? So volleyball Thursday at 5:30. Okay. Oh, it's in the middle of your MATLAB class, isn't it?
Yeah.
Are you on MATLAB? Are you in the online? Yeah, just blow it off and do the online part. There's a late lab day. You mean for circuits? Yeah, late lab day. Just put it in the late lab day. Yeah. Oh, yeah. Yeah, there's an assignment called late lab day. Yeah, just put it there. Good.
That's cool.
You can play it again. The important thing is you're jumping up and down, you're chasing after a ball. You get rid of all the stress from all I wouldn't want to get in the way of a 5 meter per second ball. The winning team.
Did you went to stop running?
I did. Did you see me though?
I saw you, yeah. I was walking by.
We're having the most amazing conversation. Did you ever talk to the owner? He's a Persian.
Rami?
He told us his whole story of how he got out of Iran.
Yeah, he had a jewelry. I come out.
He said he was selling shoes.
No, a jewelry. He had a jewelry.
Oh, maybe he's embellishing.
He was lying to you. Well, ask me.
His uncle was